If this is your first time here, this isn't a standalone video. It's one chapter in a complete story, the entire history of evolution, from the first replicating molecules to you. Every organism we mention is your direct ancestor, not a cousin species, not something similar, your actual lineage, an unbroken chain connecting you to the origin of life. That's what makes this different from every other evolution content out there. Most of it is scattered fragments, dinosaurs here, early humans there, the Cambrian explosion somewhere else, all disconnected. But they're not disconnected. They're all chapters in the same story, your story, and you can't understand any link without seeing what came before it. Lungs don't make sense without swim bladders. Mammals don't make sense without reptiles. Each chapter builds on the last, and nothing appears out of nowhere. 4 billion years of your deep history told is one continuous thread. If that sounds interesting, Chapter 1 is in the top right corner. I'd recommend starting there. If you've been watching from the beginning, you already know what this is. Let's keep going. Chemical modifications can be added that affect how the RNA behaves. The RNA can be checked for errors and corrected before translation begins. None of this is possible in prokaryotes, where transcription and translation are coupled. The nuclear membrane created time and space for information processing between reading the gene and producing the protein. Another consequence of eukaryogenesis was the evolution of a sophisticated cytoskeleton. Archaea had primitive versions of cytoskeletal proteins, but eukaryotes elaborated these into complex dynamic networks. The eukaryotic cytoskeleton consists of three main types of filaments: microtubules, actin filaments, and intermediate filaments that crisscross the cell interior, providing structural support, enabling shape changes, and serving as tracks for molecular motors to transport cargo. The cytoskeleton allows eukaryotic cells to do things prokaryotes cannot. They can actively change shape, extending protrusions to explore their environment or engulf particles. They can transport materials long distances within the cell by loading cargo onto motor proteins that walk along cytoskeletal tracks. They can organize their interior, positioning organelles in specific locations and moving them when needed. The cytoskeleton essentially transformed the cell from a static bag of molecules into a dynamic, organized, and responsive system. These capabilities fed back into enhancing the eukaryotic lifestyle. The ability to change shape and engulf particles enabled phagocytosis, actively hunting and consuming other cells. Eukaryotes became predators, eating bacteria and other small organisms wholesale rather than just absorbing dissolved nutrients. This opened entirely new ecological niches and intensified selection for traits that improved hunting, evading predators, or competing with other eukaryotes. The endomembrane system, an interconnected network of membrane compartments including the endoplasmic reticulum, Golgi apparatus, and various vesicles, evolved to manage the traffic of proteins and other molecules within the cell. Proteins destined for different locations or functions could be synthesized, modified, packaged, and delivered precisely where needed. The cell gained logistics, the ability to manufacture, modify, and deploy thousands of different molecular products in an organized way, rather than dumping everything into a common pool. Sex evolved relatively early in eukaryotes, though its origins remain somewhat unclear. Prokaryotes exchange genes horizontally, but they don't have true sexual reproduction where two cells fuse, their genomes combine, and the mixture is then divided up among offspring. Eukaryotes developed meiosis, a specialized cell division that halves the chromosome number and fertilization, where two cells fuse and their chromosomes combine. This creates offspring with genetic material from two parents, shuffling genes into new combinations each generation. The advantage of sex is genetic variation. Asexual reproduction produces offspring genetically identical to the parent, except for rare mutations. Sexual reproduction combines and recombines genes, producing offspring with different combinations of traits. In a changing or competitive environment, this variation means some offspring will be better suited to current conditions than either parent. Over time, sex allows faster adaptation and more effective responses to environmental challenges and to other evolving organisms, particularly parasites and predators. By about 1.5 billion years ago, eukaryotic cells possessed all these features: mitochondria providing abundant energy, a nucleus separating transcription from translation, an extensive endomembrane system organizing internal logistics, a dynamic cytoskeleton enabling movement and shape changes, the ability to engulf and consume other cells, and sexual reproduction generating variation. These weren't minor tweaks to the prokaryotic design. They represented a fundamental reorganization of cellular architecture, possible only because of the energy surplus mitochondria provided. Our lineage at this point consisted of single-celled eukaryotes, probably living in aquatic environments, feeding on bacteria and possibly on other smaller eukaryotes. They were larger, more complex, and more dynamic than anything that had existed before. But they were still solitary cells, each living independently, reproducing by dividing, with no coordination between cells beyond competition and predation. The transition to multicellularity, cells staying together after division and coordinating their behavior, was the next major step, but that required additional innovations beyond what eukaryogenesis provided. Cells needed ways to stick together reliably. They needed communication systems allowing cells to coordinate their activities. They needed mechanisms for cells to specialize, taking on different roles within the group. These innovations came later, built on the foundation eukaryogenesis established. For now, the crucial achievement is complete. Our lineage transformed from simple, small, energy-limited archaeal cells into large, complex, energy-rich eukaryotic cells capable of internal organization, active movement, predation, and sexual reproduction. Every animal, including humans, inherits this cellular architecture. Every cell in your body is a eukaryotic cell containing mitochondria, descended from that ancient bacterial merger, a nucleus organizing genetic information, an endomembrane system managing internal logistics, and a cytoskeleton providing structure and movement. The complexity visible in animals, tissues, organs, sophisticated behaviors, is built on the complexity established here, at the cellular level, 2 billion years ago.